I've been president of the ISSS and involved in IFSR and in systems research. I directed and founded a group called the Institute for Advanced System Studies at my university, and we used up about $5 million on systems education over the 40 years of doing research in systems. And that's all I'm going to say. Okay? So he already mentioned the title, Beyond Biomimicry to Systems Mimicry, and the subtitle is the important one. Can we use evidence from the natural sciences to design better systems? And in my last 10 years in INCOSE, I've recognized that very few of the natural sciences are used, except for those who are using biomimicry, and so that's why I thought it was important to write this presentation. The first thing we're going to cover are the tenets, which are also the benefits and contributions of systems mimicry. Then we're going to look at how it's different from biomimicry briefly. And I'm only going to give a single exemplar case study of systems mimicry. I'm sorry, but I cut out the other four. I first want to thank the Enchantment chapter, what a beautiful name, for inviting me, and Rick Dove for carefully looking over and trying to guide me in trying to reduce this so it at least lasts the appropriate amount of time, but not too much. So I'm just going to look at the exemplar case study, Hierarchies in Materials Engineering. In the paper I presented at the Conference for Systems Engineering Research this year, I had four, and I can send you that paper if you're interested, or the other ones. So the fourth thing we'll cover is systems mimicry is based on systems processes theory. So I think I should give a brief introduction to systems processes theory and its usability for systems mimicry, which is far beyond this one case study of using hierarchies as a systems process. And then I'm going to briefly look at a new tool and 4 strategies for systems mimicry, but I'm going to introduce the tool, which looks like it's based on the asknature.com. Some of you who are familiar with biomimicry know that tool online. And I'm only going to talk about the general systems theory strategy and the systems pathology strategy. I'm not going to go into network, motif, or general morphology, because I think it would take too much time. And I'm going to end with action projects for birthing systems mimicry if we get that far, okay? I'm going to stop rigidly at 40 minutes wherever I am because I want to make sure that we have time for discussion, which is the most important thing. Wonderful people from industry and from national labs to see what they think about all this. So first of all, the tenets. What's the basic idea? We're going to focus on systems processes, which are more general and not particulars. So we're talking about a generalized mimicry, not things like biomimicry. So I call it a new discipline, but actually there's a number of people, like the Natural Systems Working Group, who have this broader view. But when you look at what Natural Systems Working Group does, it's mostly biomimicry. So I want to advocate, if I can, the broadening of the concept of mimicry to systems mimicry at this more abstract systems architectural level, and not just what biomimicry does. What biomimicry does is kind of transfer from one instance to another instance. These are instances, particular solutions that have come up in biology. What systems mimicry will do is, after it's abstracted the general architectural principles of how to work as a system, how systems dynamics works across many scalar levels, is to apply those to the real systems at particular levels, human levels, for example. So in biomimicry, it copies real properties with similar scalar relations but different materials, such as shark skin for moving more quickly through fluids, spider web, strength of the fibers, gecko feet for adhesion. Velcro actually came from plant adaptation and ability of leaves to reject water or get unwettable. So these are specific biosystems with specific properties and not moving across scalar relations. Now, in systems mimicry, we compare many scalar levels to get the abstract operating relations, and we copy those, not the specific instances of how to achieve one of those desirable things in the lower left-hand corner. So in this case, what we're looking for is how to transfer the advantages of hierarchical structure or cycles or fractal structure or feedbacks or the ability to do self-organization from understanding comparisons of systems to the things we do in engineering. So it's quite a different scale, we think. So systems mimicry is at Venn circle. Biomimicry is within it. It's sometimes we do it for biomimicry. We transfer the hierarchical relations, which is the case study I'm going to look at. So let's continue. The big question is who does the abstraction for the universals and how do we do that? And I'll get to that as we get to there. So some initial tenets, which are also assumptions and working hypotheses, are these. Many engineering problems are really systems level problems. So to solve them, one way to do it is to improve the system's architecture. So not just the particular solution, but the system's architecture. Some of the most messy problems are actually hybrids of both natural and human systems. And so we need to be able to apply these general principles. And they're much more broadly applicable than the particular instances. Velcro won't help you handle chaos in engineering design. In many cases, nature is a good engineer of systems. That is a tenet. So astronomical systems and chemical systems and geological systems have their longevity and sustainability because they've solved problems. And to solve their problems, the natural sciences usually create a phenomena like continental drift or aggregation of gases for planetary origins, or for that matter, for solar systems origins, or chloroplasts, or the Krebs cycle. And all of these cases, these are phenomena that the scientists have studied for perhaps 200 years now in many cases. And most of those phenomena are systems level. So the science that studies it at great depth can be harvested by the engineers. So if chemical engineers study a lot of chemistry, systems engineers, I advocate, should be able to study a number of systems courses. And this fall I'm teaching an Introduction to Systems course to our graduates at Cal Poly in our new Masters in Systems Engineering program, for example. So I try to get them involved in the vast natural science literature, which I claim is insufficiently used in systems engineering. And I'm not talking about systems thinking. I have a series of papers that argue that systems thinking is not system science, even though many system scientists claim that, or many systems thinkers claim they're system scientists. Now, there's several working groups in INCOSE that try to integrate the systems theory and systems science domains. And so I talk about them as a spectrum of approaches that could reinforce each other. There's a natural systems working group, the complex systems working group, the systems and systems working group, as well as the system science working group. So what we do in the system science working group is we study isomorphies across all scales, disciplines, and types of systems. And we claim that the isomorphies exist in all of those different systems because they're proven useful for system sustainability. So they should be of advantage in engineering new systems. So systems mimicry would imitate natural system solutions, not just biosystem solutions. We would find patterns and processes and even pathologies common to many scales and types. So we could base our design on how systems work or how they don't work from a much broader literature database. So continuing with these benefits and contributions, we would say that systems mimicry would have a much broader range of scales and levels to explore than biomimicry because it includes the physical systems, that's geological, chemical, and complex physical systems, as well as astronomical, in addition to the bio and systems thinking, which usually concentrates on the human systems. So systems mimicry from systems processes theory is much expanded in both scope and the way it's been tested, because natural systems test their solutions immediately simultaneously and extensively. Things just don't exist unless they pass the tests of the systems around them. Now, in this case, I'm using tests differently from what most humans do. It involves humans doing the testing. In this case, the systems are testing each other. There are more variants, more iterations, more timescales represented in systems mimicry than bio. And so it would address and solve more generic problems than biomimicry. And as an engineer, I think we're moving more and more toward answering generic problems. That's what the demand is of those who are the stakeholders who want good systems. So if it's based on systems process theory, it also has much more detail because it has, systems processes theory uses that vast science literature. And it uses all the natural sciences, not just biology. And it can allow for search for unusual and unexpected solutions, ones that hadn't been thought of before, just like biomimicry offers us that. But it need not be based only on SPT. It could be based directly on any of the sciences, and I think there is already a number of groups that are doing this, like in NASA and some of the other government groups, as I will show you for the hierarchy one. I didn't start the hierarchy one. It came out of the DoD itself and NASA. So the SPT provides leverage and secret knowledge, you might say, that provides a lever by which we could move the Earth. But it requires a conscious shift from calling everything biomimicry to expanding our vision to systems mimicry, and that's what this talk is about. How are the two different? Here are the various scales of systems represented in pictures. There's 20 scales from the astronomical walls of galaxies and clusters of galaxies down to subatomic particles. Biomimicry is only going to look at those with the yellow arrows. And even then, it looks at them in pretty much a fragmented way because it looks at the individual solutions to problems. But the systems mimicry would look at all of the levels. Instead of 8, it would be looking at the 20 levels. Another way of looking at it is to look at the solutions. I already talked about Velcro and shark skin, and here's a bunch of other ways that biomimicry has added to the engineering solutions for specific things. And it's wonderful that biomimicry is doing that. I'm not attacking biomimicry in any way. I support it. I just say we should expand to look at how we could design using opposing forces or opposing functions, or how we can employ chaos functions rather than fear them, how we can maintain stability with increasing complexity of parts and maintain functionality, or increase generation of variability and decrease fracture with increasing stresses, and novel control systems, feedback arrangements that hadn't been thought of before that are used in various solutions to problems in nature. And in this chart, which you can look at some depth, I'm not going to go through all of it, there's similarities because both are based on past experiments, they mimic features of a natural system, and they're based on past peer-reviewed science literature. But there's a lot of differences. They come down to mostly that biomimicry concentrates on biodomains in that discipline and particular manifested features and solutions that bioevolution has fixed. There's one problem, one solution, while systems mimicry would look at all of these disciplines in the natural sciences and their literature, abstracted general mechanisms, and solutions that lead to sustainability long beyond what is accomplished by bioevolution. And in that sense, we would say that there are many problems that could be solved by one solution because of the generic nature of it. And then there's differences in timelines and the range of application and also the testing that's been done for it. In biology, it's mostly millions of years, but in systems mimicry, it's actually billions of years. And of course, the final one there is perhaps the most stark, particular solutions and particular problems for biomimicry, generic solutions and generic problems for systems mimicry. So basically, designs in both solve a problem, fulfill a need, or perform a specific function, or exploit a potential or find a new potential, use the former established components in a unique way, but in systems mimicry, we have a wider range of application and testing of those. Another way of looking at it is the time spans. Here's that typical contraction of the entire history of the universe in one calendar year, and that's about 13.6 billion years. Well, physical systems history is 75% of that year, while biosystems is only 25%. And if you expand the biosystems, human systems are only a very small top part of that. Social systems history and data is the target of application for both systems and biomimicry to human engineering. But humans and their systems have only been around for that last minute of the entire year. And so we should go beyond systems thinking to the natural system. Now, if your head is swimming, here's another one for you that makes your head swim, so ignore it. Basically, this indicates that there are a lot of case studies we've accumulated for this, but just look at the bottom right-hand corner. This is slide number 16, and the bottom right-hand corner indicates that about 57 or 60% of the case studies that we've accumulated for just these 7 isomorphies or generic architectures, systems architectures, the case studies account for 60%, while only about 20% are in biomimicry. So again, expanded database. Okay, let's get to the exemplar now. We have 24 minutes left before I end the talk, wherever I am, and we're only going to look at hierarchy. It's just this one isomorphy, and we're only going to apply it to one type of engineering, materials engineering. And this comes mostly from a Department of Defense, NASA study that was done by a committee on synthetic hierarchical structures of the National Materials Advisory Board of the Commission on Engineering and Technical Systems for the National Research Council. It was paid for and sponsored, as I said, by the Department of Defense and NASA. And in basically what they did here is they looked at the features of hierarchy, which hierarchies as a systems mimicry knowledge base is just one of the 110 or so isomorphies that we study in systems processes theory. So we're just looking at one. And the first thing you do is look at its features like subsumption or clustering or aggregation or significant change in scales or levels in a specific order or the constraints that operate between the levels. Or you look at how it works with other things like hierarchies are key organizers of networks. They require flows between levels. They significantly affect intra and interlevel feedback process. And once you have a picture of the hierarchy, then you try to use its qualities to indicate how you might use this in materials engineering to develop better materials. And that little figure in the bottom right comes from the materials engineering workbook, so to speak. And if you substitute systems laws for the physical laws that they usually work on, you basically get the picture of systems mimicry. So materials engineering is obviously the study, development, and testing of materials and their properties, and looking for the development of new materials with better properties, like stronger, more flexible, more temperature resistant, fracture less, so that we could use them in high performance spacecraft or smaller batteries or many other practical uses. Now, once a group organizes their knowledge on hierarchy, generally speaking, this National Research Council invited a lot of specialists in biology to look at hierarchies. But look at this bottom right-hand figure one of my students did. It's the annual council reviewed articles from a limited period, about 30 years, and it shows that the number of papers on hierarchies in the physical system, in the biological systems, and in engineering have increased dramatically across that period. So the trend for the 30-year period is quite distinct as an increase. It's from hundreds per year to tens of thousands per year. So that's a lot of literature to look at. And it even has the human sciences, which use hierarchy the least. You might think that's not the case. Oh, but it is the case, ironically. So one of the examples is tendons. This is an example of one-dimensional fiber hierarchies. There's many inside the cell, like microtubules. I know that pretty well, and neurons. Anyway, tendons have complex material property requirements. They have to be stiff to transmit the force, but they have to be elastic also to allow for movement. How do biological systems do this? Well, one of the ways they do it is by hierarchical structure, because testing of it shows it distributes the stress and minimizes the risk of failure, something that you would want in materials. Another is tendons, but in this case, they looked at the failure of tendons, and they found that basically what happens is when the hierarchy is disturbed in tendons, then it leads to failure. So there's something about the hierarchical structure itself which leads to its abilities in tendons, or as we saw in the last case, to be able to support and increase longevity. But that's a biological example. You can use hierarchies in wood and glass. Wood cellulose is composed of microscopic cylinders that are oriented parallel to the trunk, and they provide stiffness. But at the same time, they reduce the amount of fracture because of their individuality and because of the controlled orientation of cylindrical cells. If the cells fail, they'll do so in a direction that does not encourage fractures across the whole complex, the hierarchical complex. And this is exactly true for glass and for metals too. So hierarchical structure reduces vulnerability to fracturing stress. And so it's the general thing. So they summarized their findings in the National Research Council and found these dozen potential uses of hierarchy in metals, ceramics, polymers, and hybrids, involving these dozen needs and solutions. Now, these are not my list. My list is 26 of hierarchical functions that an engineer would like. And I don't have time to go through them, but these are the ones they did independently of looking at the systems processes theory and how we find isomorphies of hierarchy between many different systems. I'm going to go through just a couple of these because we only have 19 minutes left. Recurrent use of constituents in hierarchies, hierarchical controlled orientation, durable interfaces, increased variation in properties because of hierarchies, the role of water, fatigue resistance and self-repair, shape control, 1, 2, and 3-dimensional hierarchies, hierarchical basis for mechanical behavior. This is slide 24 in case you want to ask a question about it later. Hierarchical basis for synthetic processing procedures. Hierarchy actually helps in self-assembly. And then you could compare with hierarchy-based biology processing in order to do engineering processing. This is the reference at the bottom right-hand corner for that 130-page book, as I recall, on use of hierarchy. But this is just one of the 105, 110 different systems processes in the systems processes theory. We just used one of those, hierarchy, and what you might want to imagine is using hierarchy for other engineering disciplines in addition to mechanical engineering, or using the other isomorphic systems processes. So I hope this case study gives you a sense of the breadth and scope that is possible for systems mimicry. It's a spin-off of the systems processes theory, and there's many spin-offs. I'm going to mention systems pathology at the end, artificial systems research, systems allometry, applications to public law, and then systems mimicry. These are all ways that you can use systems processes theory. So it really is a theory. There are 10 uses for it. Well, that brings up the question, what is systems processes theory? I don't have much time to talk about this, but look at these objects. From the galaxy, which is a natural thing, to subatomic particles, those are quarks there on the bottom left, cells, molecules, biomolecules, which are macromolecules, to an astronomical system. Huge amount of differences here. What do we mean by isomorphy? When you study these on the surface, these many objects at different scales in the universe, they originated at different times, and they appear to be very, very different. Some are man-made, some are not. But when you go beyond their particulars to their general dynamic structure and function, when you compare them, as you compare them, you begin to see that some of them, many of them, exhibit identical key processes and dynamics. So we could call these universals, but that would be kind of pushing it, I think, too far. So we call them isomorphic systems processes, and that's what we study. And I can't understand why people from these various sciences, geology, biology, chemistry, physics, computer science, astronomy, why they don't ask the question, if the origin times and the mechanics of origins and their component parts are so completely separate and different from each other, why do you still find that they have similar processes? I mean, that should challenge any scientist. But you know what? Astronomers don't talk with biologists and chemists and physics. They don't talk with each other, and so they don't even know about these comparisons. That requires a different mindset. What we claim in systems processes theory is that nature starts with all kinds of chaotic systems and falls into these processes. So if we look again at the 20 different levels, we find that they have cycles, hierarchies, they have feedbacks, they have fractals, flows, networks, synergy, duality, they have symmetry. There's more that I can name. And they have them all the way across all of these natural systems. The reason we don't see this is because we tend to have broken up the world like a butcher breaks up a chicken or a calf or a cow in order to be these different disciplines, biology, geology, and sociology. And those are the things we fall in love with, but we could fall in love with feedbacks or self-organization. We can have departments of self-organization and departments of feedback instead of departments of biology and geology. You get the idea? So systems processes theory comes up with these systems processes, which we regard as hypotheses, and we keep shifting them around in different numbers and different sets of them. And then we add a new level to it that general systems theorists back in Bertalanffy's time didn't do. Bertalanffy suggested this, and Norbert Wiener followed it up with feedbacks and created cybernetics and so on, but they never had linkage propositions, which are formal statements in a language that tell how one system's isomorphy affects another one. These are the linkage propositions. And we call them propositions so people don't believe that they're absolutely proven, but this results in a very rich detail of how systems work. And since the processes have steps in them, we can also start to talk about when steps are left out. And what happens in that case is usually a dysfunction. So we can talk about an organized systems pathology, which is extremely rich. And so these are the 20 key contributions of the systems processes theory. And one of them, of course, then would be systems mimicry. But I'm not going to go over these now. It has many more isomorphies and adds the linkage propositions. But here's 22 things that it adds to systems theory. This is a picture. Each one of the blobs or spheres in this case are a systems process. And those lines are linkage propositions of how one interacts with the other or influences another. Here's a later one, which is more complicated, but I think you begin to see I hope you begin to see the richness in the underlying theory. And that's what systems engineering keeps talking about at these various meetings of INCOSE, IS, and CSERs. Just like chemistry has a wonderful chemistry knowledge base, we need a systems knowledge base. This is the systems knowledge base they should be using, not just systems thinking and management. So there's a new tool and strategies for guiding systems mimicry. We're toward the end of the talk here. I'm actually going to finish, I think, ahead of time, which, Janet, is one of the first times you've ever seen that, probably. I would like to create an online tool that is like Ask Nature. And this is the old Ask Nature. Now, it's actually 2 generations ago that they had an at-a-glance format, all in one page, that I thought was very impressive and useful for engineers. It was fairly arbitrary and had experiential categories, but I liked the early groups more. The early groups said, you want to solve a problem in wetting? You want to create less friction? You want to increase fiber strength? You want flexibility with no breaks? You want to get better adhesion? And that led you to various species which had solved that problem, and that's exactly what they've been doing for biomimicry. But this is what the charts look like. Nowadays, they say you want to make, you want to process information, and it goes into more and more detail, and more detail eventually it gets to the individual species solutions. This is more of the same. So it's what I want to do for systems mimicry is this. I've got green or orange, or I'm not sure, I'm colorblind. Insert here at the top systems processes as the major taxons. And then in the second subgroup, set up their identifying functions. So what do you want to do as an engineer? Do you want to solve a problem with hierarchy? Do you want to do some of these functions of hierarchy? Do you want to achieve durability or self-healing or responsive to changes in the environment or parsimony or enable variation potential or self-assembly or more stable assembly processes or tame complexity while using it or enable greater information density or increase exaptation? Those would be in the bottom part in the pan here. And so it would lead engineers to be able to use the tool to get to the way to the strategy to use in the engineering. That would be the tool. And you could do the same thing with systems pathologies. You could put the major taxons based on the isomorphies and then put down the specific dysfunctions of each class. Once you know the process, like in feedback, you can see ahead of time the way the feedback would dysfunction. And you could predict whole classes, sets of dysfunctions or diseases that happen in many systems. And it might be the same dysfunction that happens in a biological organism, in an ecosystem, or in an industrial application, in a product, or in an enterprise. So we can use systems pathology as one of the strategies. And because we have the systems processes theory, we can look at the problems that would occur in feedback, and that would be cyberpathology. So it's a whole class of diseases. Each of those clouds is a specific disease, and there's 7 there as examples, but we could come up with 20 more probably. Or cyclopathologies, or one can talk about nexopathologies. And this is modeled after the successes of medicine over, well, 2,000 years, because it goes back to the Greek time. Rheopathologies, errors in flow. Heteropathology would be problems with hierarchical structure. So we have 50 classes of pathology. So systems mimicry would use knowledge of pathologies to anticipate and to fix errors of design. This is the last 2 slides, and I have 8 minutes for 40 minutes, so I'm going to be able to stop early. So the first thing to emphasize is that you can't free the mind of engineers and general people who are working on social systems unless you visualize systems mimicry beyond biomimicry. That's the whole message of this talk. And that requires a conscious effort and a learning effort, because you have to learn the details of how systems work, which of course we advocate for systems processes theory, but there's other ways of doing that by going into the literature. But to go into that natural science literature that actually combines astronomy, chemistry, physics, biology, and geology would take a lot of time. So that's what we're trying to do for you with systems processes theory and the system science and natural system working groups and INCOSE. So action projects, I would suggest, would be like these things. First of all, populate that access tool. That access tool, if it was started to be used by people, would probably convince them, oh, yeah, this is useful because I can do it to solve this particular problem. So we want to provide an upfront taxonomy of general systems functions tied to each isomorphy and its application. We would want also a relational database. For example, in this course that I'm giving in the fall, which could be a MOOC, incidentally, but no one has asked me to do it. That's a, what is it? Massive online open access course. I actually have 90-minute presentations on just a select 7 of about 12 information or 20 information categories we have for each of these isomorphies. We're collecting for each of these. But we want to make a relational database. In fact, 3 people, 3 systems engineers, well, 2 systems engineers and I are trying to create a relational database that will be open to anybody on any of these isomorphies. You already have thousands of data and thousands of articles, and the point is to try to put them in an accessible manner. We also would like to write a systems mimicry book to cause this change in perception, but it also needs to be a change in education. The systems engineers, sustainability experts, even public policy people should take a course like this. But first, it has to be announced. And so the systems mimicry book would be modeled after some of the bio books, like Venus did one on self-organization in biology. And each chapter was an expert who discussed a case study in self-organization. Very powerful book. But we would like to do that for systems mimicry. And usually these collections have editors, but then they have authors of each chapter. So, do you want to do this? Write me and suggest a chapter. The other thing we're doing is starting an international society for systems pathology, because it doesn't exist. Systems engineering has had error and sensitivity and failure analysis, and so has the insurance industry for a long time. Medicine has had pathology for a long time. Systems biology is investigating pathology anew. So all of these domains are really talking about systems pathology, but they haven't compared across what they're doing. So we're setting up a society to do that. It's already underway. We have an international business office that's secured for 2 years. We've written and passed the bylaws. We have the first officer, and we're writing a manifesto. We have a board of directors that's appointed, and we have founding members. You could become a founding member of it by just writing me. And then I'm trying to write 2 systems texts. One describes systems processes theory as the other theory of everything, and the other, it has chapters on system mimicry and systems pathology, because it has chapters on all the spin-offs. But those, I hope, will develop into their own books in the future. And there's another one, Introduction to Systems Awareness, which discusses the similarities and differences, the potential for cooperation and for conflict between systems thinking and systems science. All of these 5 above actually contribute to each other and enhance each other, and so have a synergy between them. And basically, that's this talk. That's the end.